Welcome back to the Home Lab, and today I've got another interesting video for you. What we're going to do is we're going to look at the circuit diagram and see how it works for my little EE08 2-transistor radio build. So, as some of you will remember, a while ago I did a video on my Philips EE08 kit and we built the 2-transistor radio. I tried it out at home and it worked a bit, but there was an awful lot of interference. So we took it out into the field and tried it there, and it worked really well. But as a number of you commented, I didn't really show you very much of the manual that goes with it, which is an excellent instruction book, and as many of you remember, it's probably one of the best kids electronics kit instruction books that was ever printed. I also didn't spend any time, because the videos were getting quite long, on what the circuit was and how it worked. So for those of you not so familiar with these kind of transistor builds, you were perhaps left in the dark a little bit about what was actually going on in the circuit. So what I thought I'd do today is repair that mistake and make a little video on how the circuit works and what each component actually does. But just before we start, I want to say a huge thank you to all of you for supporting my channel, and particularly with this project and series of videos, the fantastic comments that you've left. I found it absolutely wonderful to read your stories about how thrilled you were when you received these kits as kids, and how it led on to a brilliant career in perhaps in electronics or telecommunications or engineering in general. And I'm glad most of you got them to work. I also want to say a huge thank you again to PCBWay for sponsoring this video. And as you know, they just let me do whatever I want to do, which I find is absolutely fantastic. It's well worth having a look at their website, because they've got a projects page, and on the projects page they have Project of the Week, and that actually might get you started on some ideas if you're struggling for something to do. There's also a series of videos on bits of electronics and how they work, and also printed circuit boards and the different types that you can get manufactured, and I think some of you might find that interesting as well. But I've got a little challenge for you today. As you know, these kits were built on these cards that Philips produced, and we used the 2-transistor card. And I think it would be absolutely wonderful if one or two of you had a go at actually making a circuit board layout like this. You could get PCBWay to make it for you, and then you could actually have circuit boards that are the same layout as these cards, and then maybe build some of the old physics and electronics projects that Philips had in their kits. If you manage to do that, do please let me know, and I wouldn't mind actually featuring a video of that on the channel. But I think it would be an absolutely fascinating project to do. So now, let's get on with the video. Let's start off with a quick look at how AM signals work, how they're transmitted and how they're received. And if you know a great deal about this already, you might want to skip this bit, though it might be interesting for you to see how it's taught if you're someone who knows how it works but you've never had to teach it to someone, and the simplifications you can use to explain the principles that are being used in AM transmission. So we all know that AM is amplitude modulation. So the first thing you have to understand is amplitude is the height of a wave. Now, it's often confused. I notice on YouTube they confuse the amplitude as being from peak to peak. It isn't. The amplitude of a wave is defined as 0 to the highest point. So it's actually from here to here. Once you know that, you can then understand how AM signals are transmitted. So the first thing to do is to have a sound wave. So you need a microphone and some way of converting sound waves from a mechanical wave to an electrical one, and you'll get a varying signal. Now, agreed, this is AC, but it's not very high frequency, because sound, if you're speaking, is in the range of, well, we consider it to be about 20 hertz to 20 kilohertz. So let's say our sound is in the region of about 1 kilohertz. It will vary in frequency, as with this diagram I've drawn, and in amplitude. Now, when you're teaching this, it helps to imagine that that signal then has a DC voltage added to it. So it pushes it up on this scale. It's not really important to really understand why I do this and how it's done, but it really helps you understand the next stage. So that's going into our transmitter, but inside our transmitter is an oscillator that produces a very high frequency of constant amplitude and constant frequency. And we call this the carrier. And the carrier is basically the frequency of the radio station that you're listening to. So let's go for 100 kilohertz. So that's a frequency 100 times higher. Now, I haven't drawn this wiggling 100 times more rapidly per second, but you get the idea. So we've got our varying sound wave, which is getting really close almost to DC. It's quite a low frequency. And we've got a very high frequency carrier signal being produced in the transmitter. And what we've got to do is add these two together. Now, I'm being really careful about what I say about adding here, because it's best to consider these systems a bit like amplification as a multiplication. Now, I won't get into the maths, but if you can think of taking every value of this carrier and multiplying it at the same time with the value here on this wave, the sound wave, what you'll end up with is a shape like that. Now, one of the reasons for pushing this up a little bit is because all of these values are positive now, which means that if we multiply them with all the carrier values, the ones that are positive will go higher and the ones that are negative will go further down. So you end up with this sort of a shape, if you see what I mean. Okay, which means you sort of see the sound wave on top of the carrier and also below it. Okay, that's just one way of explaining it. Right, so we've now got one signal here, which is a carrier wave, very high frequency, varying in amplitude. Okay, you don't actually see this sound wave. If you look at it on an oscilloscope, you just see this varying amplitude. Now that can go into a transmitter, be transmitted out into the ether, as it were, and then received by a receiver. But here's where it gets a little bit fiddly. And those of you who are very familiar with crystal sets will realise you need some kind of tuning. Now, why do you need tuning? Well, there's two reasons, but the main reason is there'll be other stations transmitting at other carrier frequencies, maybe 90 kilohertz or 110 kilohertz. And your antenna sticking up into the sky is going to pick up all of them. So what we then need to do is feed those very varied signals into a simple circuit that picks out only one. And again, I won't go into the details of it here, but typically these are a coil of wire in parallel with a capacitor. And that has a particular resonant frequency. In other words, it has a frequency that it likes to oscillate at. And so it will pick up only the frequency that it likes to pick up. And you set the capacitor to this carrier frequency. So out of it, if you tap out of it, usually a position on the coil, you will get the signal that was transmitted and not the others. Okay, they've been rejected, not totally, but again, that's quite complex. But the one that comes through best is the frequency that you've tuned to. So you'll set this up, in our case, to pick up 100 kilohertz. So we've now got a very high frequency varying wave. Remember, it doesn't have sound in it. It's just varying at a high frequency, but the amplitude is changing in the same way our sound signal changed. So a good way to think about this is that our amplitude shape here is almost DC, whereas our high frequency is definitely AC. So feed that through a diode. And again, those of you who know about crystal radios, that could be a germanium crystal or something that only allows current in one direction. And you'll strip out the AC part, the high frequency part, and leave the bit that looks really like DC. Okay, massively simplified, but you get the idea. And there's filtering that can go on and all sorts of other things. But if it's a crystal set, we go straight to our high impedance headphones. And in a more complex radio like the one I built, there's a little bit of amplification and there's a little bit of filtering as well to make sure this works slightly better. So that's a sort of simple way of explaining how amplitude modulation works. You might want to look up FM, frequency modulation, if you're interested in this sort of thing and it's fairly new to you. But you'll see sound, modulate a high frequency carrier, transmit that, pick out only that frequency, strip out the carrier, and you'll be left with the sound or the audio, and then do what you like with it. Feed it probably into an amplifier or directly into some headphones. So now we understand a little bit about what AM is and how it's transmitted and received. Let's have a look at the kit again. So if you remember, the Philips kits, both the EE08 and the EE20 came with the same instruction book, and it's absolutely fantastic. And I think many of you commented that the instruction book is one of the best you've ever seen. And even on its own, if you haven't got the kit, if you just had this, you could learn a huge amount about electronics. It was beautifully made and really well translated. There are a few bits that are a little bit odd, like instruction book. I don't know if that's exactly meant to be capitalised on one word, and maybe it's two words, who cares? And the book almost looks like it was added later as a sort of slightly different typeface. But I'm being picky here. It's also interesting to note that the Philips logo, I had it pointed out to me in very strong terms that Philips always use capital letters in their logo. And indeed, in their logo they did. But to give you an example, there are times when Philips used lowercase when they were talking about other things. So yeah, there's their logo, but here are the resistor colour codes, and there's Philips in lowercase. And there are examples of this in various places. There's a wonderful Philips logo in the railway station, and it's absolutely massive. And I saw that when we were visiting family in Germany. Anyway, I digress. So inside here, you've got details of how to build the radio, if you remember, but they only show a picture of the one transistor radio, and then do a little bit of explanation about how to build your reception ferroceptor coil and a wire antenna, and how you could use it for direction finding, and then it just tells you to sort of get on with the two transistor radio. But if you turn to the back, working through all the excellent bits that explain how electricity works, you've got some circuit diagrams, and it's those circuit diagrams that we can look at today, and particularly this one, which is the one I built for the two transistor radio. So we'll have a look at the card that we built it on, we'll have a look at the circuit diagram and how it works, and I'll show how this has been transferred to the components of the radio I actually built. So the bit you've all been waiting for, the actual circuit that Philips suggested you built to get your two transistor AM radio working. I've blown this up from the instruction manual, and I rather like it because it looks like a blueprint, which is really fun. And I think as a kid, I would have really enjoyed that sort of look rather than just the black lines, as it were. So I could explain this by doing the single transistor radio first, but it's easy just to go straight in and do the two transistor one. So it consists of a number of parts: antenna and reception and picking out the right frequency, a transistor to do a little bit of amplification, a diode to get rid of the carrier wave and allow only the audio, and then all of this circuit here, apart from the power supply, is used to amplify that even further. And the bit I've covered up with my hand is the bit you don't really need, because that's to create a stronger signal so the headphones can work well. And so it would work as an audio amplifier, whereas here we're actually amplifying the radio signal and, interestingly enough, the audio signal too. It's really clever. So this arrangement is called a reflex receiver, and I'll explain why it's called reflex in a second. So let's look at how it works. So here's our wire antenna coming in, and we had about 4 turns of wire going from the antenna down to earth on our ferrite bar, on our ferroreceptor. Now this is really clever, and I won't go into the physics in detail, but here is that tuned circuit I was talking about, and you'll notice that it's not really connected to anywhere, it's just connected to ground. So you need a little bit of physics to understand this. The radio signals coming in will be of a whole range of frequencies, as you know. The carriers will be all different frequencies, and that will cause magnetic changes in the ferrite bar. But the ferrite bar links those magnetic changes to this system here, and this is tuned. And tuned circuits are like running your finger around a wine glass. They oscillate really well, they absorb energy really well. So this, if tuned to the right frequency, that's the one we want to pick up, that was the 1 kilohertz in my previous diagram, will oscillate really well and create changing magnetic fields in this ferroreceptor that can be picked up by this second coil here. So consider it to be almost a transformer. So all signals coming in, stripping out the tune signal and making that really strong, picking it up with this coil and feeding it into the base of this transistor, and that's the AF116 transistor. So we get some amplification, and the signal, remember that's the high frequency carrier with its amplitude modulating, coming through here and hitting an inductor and a resistor. Now this inductors don't like change. They don't like, they're like heavy masses. They don't like change in current. So the current instead will pass through this capacitor. The capacitor also has an effect of blocking any DC that gets into that system, and then through the diode. Now we know what the diode does. It strips out that very high frequency component, so it demodulates, and then off it goes to the headphones. No, it doesn't. This is really clever. This is the reflex bit. We've stripped out the carrier, so the audio now goes back into this coil, okay, back into this transistor, the AF116, and gets amplified again. So that's really clever, and if you understand that, you understand reflex circuits. So we've now got also coming up here, after its first pass through the transistor, a low frequency bit of audio. Now, because that's not high frequency, that can pass through the resistor and particularly through the inductor. So off it goes. Again, a bit of DC blocking here and through this variable resistor and down to ground. So you've got the audio here, the sound. You could consider the whole voltage to be across this potentiometer, and then you can take off none of it, some of it, more of it, or all of it, and feed it, blocking capacitor again to strip out any DC, into this transistor, the AC126, onto the base, and that base will have a small current flowing through it. This transistor will amplify that current, and here it is coming down to here and through your headphones. So it's a very clever little circuit, but it works really well, and it's typical of all these reflex AM radios. So just before we finish on this, let's have a look at the cards. Here's a copy of the 2 transistor card, and I'm looking behind me. Here it is. Here's the 1 transistor card, and we'll have a quick look at that first. So I won't spend a long time on this, but that's what we could have built. And if you look at that, you can see that that's a reflex circuit. You know a lot about those now, with the antenna bar here and the coils on it, etc. 1 coil there and 2 here. We can see the signal coming through, the diodes there, the base of our transistor is here. There's our inductor passing only the low frequency and coming out, and the potentiometers and things are down here, and the battery connections are there, coming out to our earphone. But of course we built the 2 transistor version, so isn't it, I mean, most of you who are watching, I'm sure you're really brilliant at this and you know more about it than I do. But if you're a beginner, isn't it interesting how you can break things down into these parts? And if you're nervous about electronics and you've wondered how anyone can understand it, you should be able to begin to see things now. You go, oh, I get it. Wire antenna, signal here, the double coil there, signal coming into a diode, signal being fed into the base of a transistor, going round again. Here's the stage that removes the AC high frequency component. In other words, doesn't allow it through here. It has to go through the transistor and through the diode instead, and then out to another transistor, and then to our crystal earpiece. High impedance, that's high resistance, I suppose, so it doesn't load the circuit, it doesn't try and draw too much current and drop the voltage too much. Output here for the sound that we want to listen to. So finally, now you'll know it all makes sense. So here's the little radio that I built. And again, if you're a bit of a beginner to electronics, it all just looks like a tangle of spaghetti and snakes. But in fact, you can now see the main parts of the circuit. So the power supply here, the circuit we've got has got amplification. So we do need some form of power supply. It's not just a crystal set. And our antenna coming in, our ferroreceptor, the coil that brings in the signal, the 2 coils that we use, to extract the signal from that. Okay, there's the diode, these lovely big glass diodes, the OA79, and the signal going through that. Here's the transistor, our AF116, and the signal will go through that, be amplified, and come back. And because it's gone through the diode, will be low frequency, will pass through this little inductor here, and then will come on and go through to the base of this transistor, that's the AC126, and be amplified. And finally, I haven't connected it, but come out on our crystal earpiece or our headset. We can turn it on and off, and we've got a variable resistor here. And the bit that I didn't really mention earlier, because it's hidden away, if you remember, on the coil, we've got that coil that selects a specific frequency by changing not the inductance of the coil, but changing the capacitance in parallel. And underneath here is our variable tuning capacitor. So I do hope you enjoyed that video and you feel now that you've got a slightly better understanding of how the circuit of the 2-transistor radio works. And do please leave a comment if you feel I haven't quite got it right. I've done my very best to explain what's actually going on this little circuit. So it's an absolutely fantastic kit, and I think what I need to do is combine it with the EE20, which has got some extra bits, and I think we need to do some more builds. So before long, I'm sure there'll be another build of this kit coming to you on a video. Anyway, as ever, do please leave some comments. I always find them absolutely fascinating to read. And as you know, join me soon because I'll be making another video before too long.